Thank you for joining for tonight's Marston Theater Virtual Night Sky presentation. My name is Kim Baptista, and I am the Alumni and Special Events Coordinator here at the School of Earth and Space Exploration at ASU. And I will be your host this evening while Rick is away on vacation. Joining me in the background is Meg Hufford, my colleague, and two of our students, Alicia Hyatt and Alex Blanche. And tonight we are joined by two guests. We have Lawrence Garvey, curator for the Center for Meteorite Studies, and Nick Estes, Science Operations Manager for the Lunar Reconnaissance Orbiter Camera Team. And also we will close out tonight's presentation with some current ASU missions, exploring asteroids, share some upcoming events, and share some links to the resources from tonight's presentation. And I also have some housekeeping things for you. Before introducing our guests, tonight's format is a Zoom webinar. Their presentation will be approximately about an hour in length. And then we ask that you leave questions in our Q&A box, and we will do our best to answer all of them. For best viewing, please switch to full screen, and that can be found in the upper right-hand corner of your computer screen. We also have a live transcript that we will be having this evening, and you can also disable that if you would like to not have that present on the bottom of your screen. And with that, I am going to introduce our first presenter, Nick Estes, and I'm going to let you take it away from here, Nick.
All right, thank you. On my screen here. So my name is Nick Estes. I'm the Science Operations Center Manager for both the Lunar Reconnaissance Orbiter Camera and ShadowCam. And so I'm going to talk a little bit tonight about first light for LROC, and then a brief introduction into what ShadowCam is. So the Lunar Reconnaissance Orbiter launched 12 years ago. It was June 18th, 2009 on Atlas V rocket. Because the moon's awfully close by, it only took us about 3 days to get there, and it was inserted into a polar orbit of the moon where we've been observing ever since. So LROC itself is one of 7 instruments on board LRO, and it's composed of 3 different cameras, but we're going to talk only about the NACs, our narrow angle cameras tonight. So the NAC telescopes are constructed from carbon fiber. We have this diagram on the right. And the telescope and sunshade components are all made from carbon fiber for 2 reasons primarily. It's lightweight, and it can withstand the strong vibrations from launch. The downside to a carbon fiber structure is it absorbs moisture from the air, and it actually physically changes size, which means here on Earth, where we're testing the camera, it's out of focus. So once we're in space, we actually have heaters that are wrapped around the telescope, and those heaters run for a week to drive the moisture out of the carbon fiber structure and bring the camera back in focus. And so what first light is all about is the first camera the first image these cameras take after the bakeout period. And it's a very important image because the science team needs to be sure that enough moisture has been baked out of the carbon fiber structure, and that the mirrors inside the telescope and the focal plane of the camera itself are lined up properly so we can get images that are in focus. The ideal image for this type of focus check is something where you've got a very high contrast area between a brightly lit surface and something very deeply shadowed. And this image on the right is actually the first image that we took with LROC 12 years ago when we were in flight. This image was taken on June 30th, 2009. And the crater you see with the illuminated rim at the bottom is Shackleton Crater, which is right at the moon's south pole. What made this area really useful for first light is Shackleton Crater is permanently shadowed. So no matter what time you arrive in orbit, and no matter how your orbit is lined up at the moon, you can take an image of Shackleton Crater and always have a brightly illuminated rim with very deep shadows in the middle of the crater. So it makes a great target that you can count on for this type of image. Now this long strip of an image is actually about 25,000 pixels wide and 50,000 pixels tall. So to see this image in full resolution, you'd have to stack 25 4K TVs on top of each other to see it in high res. But we can zoom into a portion of it here. So horizontally across the screen is the rim of Shackleton crater. And we can see all the brightly illuminated rim, the pockmarked with much smaller craters. There's even areas towards the center of the image where you can see some boulders on the slope going down into the crater. And as you can see from this first image that we took with LROC, the science team was very excited. We have very sharp transitions between bright and dark areas. And so this image showed us that we were definitely in focus and ready for our long mission at the moon. So I'd like to talk a little bit more about what these permanently shadowed craters are. So the Earth, as everyone's probably familiar, tilts at about 23.5 degrees. And this tilt is what causes our seasons. And anyone who's gone outside today certainly knows that we are getting a lot more sun now than we do in the winter. And that's because of the axial tilt. The moon, on the other hand, only tilts at a very small 1.5 degrees. And so craters near the poles never angle towards the sun far enough to let light get into the bottom of them. So there's craters near the poles that never see any sunlight at all. Now, to find these permanently shadowed regions, there's a couple of ways you can do it. One is to use something like a laser altimeter to build a physical 3D model of the moon and then do a lot of math. The other way, which is a lot more fun and interesting to look at, is to build an illumination map. And to do this, we take images over the poles over time in different lighting conditions, and we combine these to find out when each area of that surface around the pole has light and how much of the time it's dark. And because of the small tilt of the moon, in addition to some areas inside the craters never seeing any sunlight, there's also some tall peaks that are almost always lit. And the illumination map can give us both of those pieces of information. And these areas are exciting for exploration. If you're sending a mission that's powered via solar panels, which many spacecraft and rovers are, these areas that see illumination almost 100% of the time are fantastic for charging batteries. And then these areas that never see any sunlight are the areas where volatiles are likely to be found, such as water ice. And you can use ice, of course, to help life support for astronauts. You can also convert it into rocket fuel. So there's a lot of potential for exploration. And so we can kind of take a look at the process of building one of these illumination maps. And so this sequence of images is all of the NACs we took over the South Pole for about the first 3 years of the mission. And instead of trying to mosaic it together like a map, we're actually taking the brightest pixel of every image as we go around, and we can kind of fade into what an illumination map actually looks like. And we can take a closer look here. And so this map, this large crater in the middle is Shackleton crater, which is what we took as our first light image for LROC. And the darkest areas see no sunlight at all. And the brightest areas of this illumination map see sunlight up to something like 93 or 94% of the time. And so some of these areas where we have permanently shadowed areas directly adjacent to these areas that see a lot of sunlight are really useful for exploration. You have the potential of having a source of power right next to where you need to do your exploration. And of course, one of the big questions is what is in these permanently shadowed craters? There's various instruments like radar instruments, gamma ray spectrometers, that sort of thing that can get signal inside of the permanently shadowed regions. And there's been some detection of possibilities of water ice or other similar things. But they disagree a little bit on what you might find where. And so the data set we really need is a camera. We need to be able to take images inside these permanently shadowed regions as something to kind of tie these other data sets together and put them in the right context. Now, these craters, they don't get any sunlight at the bottom, but they still get a little bit of illumination. It's called secondary illumination. And so that brightly lit rim of the crater actually reflects sunlight down into the crater. A good way to think about that is like in a movie theater, when they turn the lights off, the reflection that comes off the projector screen is actually enough where you can see to get around inside the theater. It's not a lot of light, but it's enough where if you have the right kind of camera, you could get a really good image. Inside the permanently shadowed regions, it's the same idea, just on a much larger scale. And as it turns out, ASU is working on such a camera. So in cooperation with the Korean Space Agency, where ASU was working to make a camera called ShadowCam. This camera is based on the narrow angle camera that we have with LROC, with a couple of significant changes. These changes are slightly bigger pixels. At 100 kilometers, the narrow angle camera has a pixel size of about 1 meter. ShadowCam will be about 1.7 meters. The other change is the sensor type. We're using a specialized sensor called a TDI, a time delay integration sensor, that can basically multiply the exposure. So we're going to end up being roughly 200 times more sensitive than the NAC. And so that reflected sunlight from the rim down into the permanently shadowed areas of these craters is going to be enough that we can take images almost as if it's daylight. And so this data set is going to be really useful for exploration, so we can find some of these volatile materials. There are upcoming exploration missions that are trying to explore the South Pole, and being able to get images inside these permanently shadowed regions can perhaps tell us where we can send rovers or other exploration to look more at what's in there. And so we're currently scheduled to launch sometime next year. And we will definitely be announcing when we have images and other things. So keep an eye out for images and news over the next couple of years, and hopefully we can get some answers to what's inside these permanently shadowed regions. Thank you. And if you have any questions, we can take a couple of questions.
Thank you so much for that wonderful presentation. Thank you, Alex. All righty. So we actually have a couple of questions, and our first question is, how deep do they think Shackleton Crater is? And that's from Kathy. So if maybe you could give us a rough estimate on that.
I don't have that number off the top of my head, but we do know exactly how deep Shackleton Crater is. One of the other 7 instruments on board the Lunar Reconnaissance Orbiter was a laser altimeter. And because we're in a polar orbit, things like Shackleton that are very close to the pole, we actually have very good laser altimeter coverage of. So we know not just how deep it is, but we have pretty good 3D models of the shape of the inside of that crater.
Wonderful. Thank you so much. And another question we have is, do you have an estimate on how much longer LRO will last for, or the LROC camera?
We don't know. There's a lot of factors that go in here. Obviously, as things age, we can't go there to do any repairs. But currently, everything on board LRO is operating really well. And we potentially, in our current orbit, have enough fuel for maybe 6 to 7 more years. So, fingers crossed, we'll be doing this for a while longer.
Wonderful. And our last question is from Chad, who says that the photos are incredible. What kind of artificial light can be used to recreate this look? So what can someone at home maybe do to recreate or to get these images that we're seeing here? Can we use like an at-home telescope of some sort?
And to recreate these sorts of images, you could do it in a computer, essentially, is how it's normally done. You can load a 3D model and then create an artificial light source. We do that sometimes with an open source software package called Blender. We've been able to load our moon 3D model in that to make simulated views.
Wonderful. Well, thank you so much, Nick, and thank you for your presentation into LROC. But actually, I'm going to hop over to another camera and take the audience on another journey. So thank you so much, and we look forward to having LROC back real soon. Thank you.
Thank you.
Hello and welcome. So we have our very extensive media team here, and we are going to take you on an all-inclusive journey. This is very exciting and something we don't do often. So if you want to follow me right this way, we're going to take you on a tour. Hello. And we are here at the Center for Meteorite Studies with the curator, Lawrence Garvey, Dr. Lawrence Garvey. Thank you so much for having us here, and maybe you could tell us a little bit more about the space and what we're going to learn about this evening.
Absolutely. Well, thanks everyone for joining us. Well, welcome to the Center for Meteorite Studies Meteorite Vault. If you look around you here, we see meteorites on all the surfaces, and we have meteorites in the drawers here. We're also celebrating this year our 60th anniversary, 60 years that we've had the Center for Meteorite Studies here at Arizona State University. And it's one of the few places in the world, one of the few universities where there's such a large collection. In fact, we are one of the largest meteorite collections in the world here at ASU. And we've been curating, and what do I mean by curate? Curating is actually a very important term. It means having meteorites that we can study both, let's say 10 years ago, I can study this year, study 50 or 100 years from now. So it's important to keep these samples. These are extraterrestrial rocks. It's important to keep these samples in a safe space. I don't just mean safe from losing them, but safe from environmental degradation, for instance. For instance, if we look at some of the iron meteorites, for instance, here's some examples of iron meteorites here. This is one from Meteor Crater. This is a Canyon Diablo meteorite. See the sample here. It's a bit rusty on the outside because it's been sitting on the ground for about 50,000 years. That's when we think the crater was formed. But if we look inside these, they're shiny metal. And those shiny metals that can actually rust here on Earth quite rapidly. But keeping it in an environment like this is a low humidity environment, we can actually keep these samples safe. We can actually curate them for extended periods of time. And we also have even more stringent ways of keeping our meteorites safe. If we come back here, we see these cabinets here. These are actually nitrogen cabinets. These are cabinets that are filled with pure dry nitrogen. And basically that stabilizes them completely. They're out of the atmosphere, they're out of the water that's present in our atmosphere. So for instance, for certain types of meteorites, which we'll talk about in a few minutes, this completely preserves them here on Earth. And that's what's really, really important. So that's what we mean by when we say curate. In fact, I'm going to have our tech person, Alec, just move up a bit, keep going back. I want to show another meteorite. In fact, what I'm going to do first, another thing that's also important, I'm actually going to put some gloves on, because however much we clean our hands, our hands are still dirty, and we shouldn't really be touching the meteorites with our hands. So we always wear gloves. So it's not to protect our hands. Like typically if you're in a chemistry lab, you put gloves on to protect your hands from the chemicals. Here we're doing it the other way around. We're actually protecting the meteorites. So I'm gonna, oh, this one tore. We're gonna have you move back a little bit further. I'm actually gonna get a meteorite out of here. And this is one of my examples, which I love, because this was a meteorite that fell. I'm gonna show you the label before I show you the meteorite. This is just a fragment of it. Let's see if you can see that. Is that focused nicely? Can you see when it fell? It fell in 1492 in what is now France. So just think about the level of science that could be done in the 1500s, 17, 18, 1900s, and now, and the ever increasing ability to analyze these materials and sort of delve into, tell us what these things are made of and what they're telling us about our early solar system. So this is just an example. This is just a small piece of that meteorite called Ensisheim. This is just it's just a rock, it's a stony meteorite. But so we think about the levels of science we can do now versus, let's say, 100 years ago or 200 years ago. But now let's project into the future. What about the science that we can do 100 years from now? So curation, so the safe curation of these materials is absolutely paramount, absolutely important. Let me just put that.
And along those lines of safe curation with the gloves, maybe you can talk about the chain of command when it comes to the name tags, or you were mentioning earlier how the name tags are very important when it comes to telling.
You know, when we talk about meteorites, there's two basic names. There's the popular name. So let's say, and this hasn't happened yet, at least not in recorded history. Let's say a meteorite were to fall in Phoenix tomorrow and be picked up and classified. It would be called Phoenix, but we haven't had one. But so that's the sort of the common name that we refer to. But if we take, for instance, this one's called Allende. So this one fell near the town of Allende in 1969. That's the common name. Whereas if we look at this one here, this one's called Arispe from Mexico.
It's an iron meteorite, but it also has then the chemical group. That's a much more sophisticated way of telling us what type of meteorite, what type of iron meteorite this is. And by the way, I say we haven't had one in Phoenix, but we did actually have a really exciting meteorite fall just about 2 years ago. Let me grab this sample. You can come this way a little bit, Alex, and I'll bring it up to here. So that's perfect there. So we actually had a meteorite fall here in the valley, surprisingly in 2018, in midsummer. It's called Glendale. So this actually fell in the town of Glendale, fell in somebody's front garden. He went out so this guy went out into his garden one morning and found this black crusted rock that wasn't there the day before. And here's actually a slice of it now. I'll show you a slice of this meteorite. This is just a slice. So fresh meteorites are often black on the outside. That's the fusion crust that forms as it's coming through the atmosphere. If you think of typically when the small asteroids are coming into the Earth's atmosphere, they are coming at a high velocity. You get friction on the outside from the stone coming through the atmosphere. That's what you see when you look up at the sky. That's that shooting star that you see, that bright luminescent shooting star that you see. And that typically only lasts, as we know, for a few seconds, because if you think about it, these things are going, let's say 100,000 miles an hour. Thickness of the upper atmosphere is only a few tens of miles. So it goes through the upper atmosphere very, very rapidly. It decelerates, it ablates. And for most of the smaller materials, they break up in the lower atmosphere, and then they slow down and drop to the Earth as meteorites. So if you pick it up, it's a meteorite. In fact, just a distinction, just to, so everyone realizes, what you see is the meteor. If you can touch it or pick it up, that's the meteorite. So in this particular case, this was a single stone that was picked up in the front in this gentleman's front garden. And if you cut it inside, it's a stony meteorite, but you can still see the black fusion crust on the outside. And by the way, what's even more exciting about this, so all of you have heard of Doppler radar, I'm sure. And Doppler radar is a system for looking for rates of change of movement in the atmosphere. That's how it sees sort of rain and things moving through the atmosphere. The Doppler radar in North Phoenix actually saw, after the main fireball came in, it was a relatively small fireball, broke up in the upper atmosphere. And as they're dropping through the lower atmosphere, Doppler radar, several sweeps, saw these objects moving down towards the ground. And when you project it down to where these things were to fall onto the ground, it's exactly in this person's front garden. We have a question.
And along those lines, Mary would like to know, how do you recognize a meteorite fragment versus a regular rock with the naked eye? So I know you touched a little bit on that, but maybe you can go into some detail.
Mary, that's a good question, and that's one that we talk about quite a lot, because meteorites have particular minerals and structures, and most Earth rocks have particular minerals and structures, or many of them do, that meteorites don't. So most of and it's unfortunately one of these things that you just have to learn by practice. And what I've said to some people who want to find meteorites, I say, go and buy some cheap meteorites from a vendor, put them down on the ground, for instance, and see what they look like. In fact, I'll show you an example. Let's have a look here. I think I have some examples here. Okay, here are some examples of what we call unclassified. So we haven't worked on these yet. Unclassified meteorites. These were found in Northwest Africa. And typically what the meteorites lack, they lack a lot of the features that we see in terrestrial rocks. They don't have any laminations typically. They typically don't have big grain sizes. They never have quartz, for instance, and quartz is one of the most common minerals in Earth rocks. They typically don't have big lumps of calcite or calcite and things like that. So it's, and I'm giving a relatively vague answer here because I can't be 100% definitive. And the best thing to do is to just literally, if you can, acquire a few of these Northwest Africa unclassified meteorites, put them on the ground, and then you will see they do look different from the way most terrestrial rocks weather. And that's really, it's only through recognition of these different samples. So here's another one, for instance. Again, meteorites almost never have structural features on the inside that are produced by, let's say, on the Earth by igneous activity or by metamorphic activity, or by sedimentary features. So we don't see those sort of things. So they weather in a sense in a much more uniform pattern. So again, I'm trying to, you know, this is one of those things where you're just going to have to get some samples and look. And it is very difficult to, without that experience, to really recognize just what we call just a cold find, just a meteorite from the desert. And this shows how rare it is actually. In the 17 years that I've been here as the curator, we have never had a member of the public bring in a real meteorite who don't already know what they look like. Never, because they almost always get it wrong. We've had people bring in meteorites, but they already know what they were looking for. So, but also to give you an idea, and this is something I'd like to impress upon people, the rarity of meteorites. So if you wanted to go out to the desert right now, and Arizona is a fantastic place for looking for meteorites, and search for what's called a cold find. So this is just like you go out to a random part of the desert and start searching. It's from speaking to other collectors and searchers, it takes on average, I think 400 or 500 hours of searching, of constant searching, before you might find something. They are actually rare, and relatively few people realize that. They're very, very rare. Okay, we can move back a bit. We have another question.
Perfect. Right along the same lines, Howard wants to know, what if 2 or more meteorites fall in the same area, or generally the same area? Do you add numbers to them, like 1, 2, or 3, or do you use the year they fell? Maybe you can discuss that a little bit.
Yeah. If you go to the Meteoritical Society, there's actually a whole series of guidelines for how you name meteorites. And this is a very specific question that you're asking here. If, and this has happened in history, that was relatively rare, if 2 meteorites fall in a relatively small area, let's say we were to have another one in Glendale tomorrow, then that one would be Glendale plus the date. So Glendale would be 2021. And there are very few examples in the literature. And we also have to define that there's also different naming conventions for meteorites. If you were to have to distinguish between meteorites here that are falls versus finds. So a fall is you're out there, there's a big event, you see a big bolide. A few minutes later, maybe there's some sonic booms and some stones drop to the ground. That's a fall. You know, that's something it's actually been witnessed. Finds are you're just out somewhere random, maybe you're searching for meteorites, or maybe you're not searching, you come across one, and that's a find. And so there's actually different, and it's a complex thing, and it's, you know, you can look at the online sort of description of how to name those, but there's a different naming convention for that. Do you have another question, or should we just continue?
If you'd like to continue.
Okay, I was going to say, you know, we just had that wonderful presentation by Nick a few minutes ago on lunar meteorites. And here, actually, this is one that we just finished classifying. Here's actually a lunar meteorite. This is actually a meteorite from the moon. So this is distinct from the rocks that were brought back by the astronauts. So they brought back, 400 kilos approximately of stones, fresh from the moon. But nature has also brought back samples for us. If you look at the moon, it's covered in impacts. In fact, LROC, I think the LROC team have been witnessing impacts on the moon. In fact, if I remember correctly, and I could be wrong, somebody's going to have to look up, there's several hundred new impact sites on the moon every year. But every once in a while, there's a particularly large impact. As you can imagine, as a large bolide comes and hits the moon, that force causes the crater to form, but also ejects material off the surface. And we're the closest object, and those things can actually fall here on Earth. And this is one example of a lunar meteorite that was found in Northwest Africa. You can look at the outside. It's a relatively unremarkable looking stone on the outside. But when you look at the inside, what you're seeing is this breccia, this welded material, these individual white mineral and rock fragments welded together by the impact process on the moon. And lunar meteorites weren't actually recognized prior to the 1980s. We had, I think there were some in collections, but they just weren't recognized. There wasn't the understanding yet that meteorites could be ejected from in this case, the moon and land here on Earth. And the same also, by the way, holds true for Mars. There have been meteorites that have been falls, and we can talk about here, we can talk about one called Nakla, fell in the early 1900s. Chassigny fell in the 1800s. Zagami is another one that fell in the 1900s. These are meteorites that we know if we cut them open and we look at them, these are igneous rocks. So they had to have formed on a body that had some true geological activity over extended periods of time. And again, it wasn't until the late 1980s that the proposition that was put forward that maybe we do have meteorites from in this case, Mars. And it took many years for that to be accepted by the scientific community. And we now know that we have a bunch of meteorites in our collections that are actually from Mars. And here's a fantastic example. This is one of my favorite examples. This is one that was seen to fall. So it's a fall. It fell in Morocco in 2011. This is one of the stones. So again, imagine you're out in the desert. It's evening or it's nighttime. There's a huge fireball. Not just a fireball. If it's large enough and you're close enough to the area, you also get the sonic booms. Because don't forget, these things are coming into the atmosphere faster than the speed of sound. So you get sonic booms. So in this case, a large bolide was observed. Sonic booms were heard throughout southern Morocco. And they saw, as it came in, they saw it fragmenting and breaking up. And within, the next day, people started to go search because they were certain in southern Morocco that something had fallen. And true enough, within a day or two, they started to find these black fusion-crusted rocks on the ground. And we didn't know at the time that they were from Mars, but the chemical analysis, isotopic analysis in particular, looking at the different isotopes, revealed this to be a Martian rock. Now, people will ask the obvious question is, how do you know they're from Mars? Well, there's a number of things that we put together, like they're igneous rocks. They had to have come from a large body. There aren't many out there that are rocky. There's Mars, there's Venus, there's Mercury. But most importantly, we've sent rovers and various to Mars that have analyzed the rocks, that have analyzed the atmosphere. And the telltale sign here really, in this case, is argon. So argon is a gas in our atmosphere. Every breath you take, you're breathing in argon. But there's different isotopes of argon. And if we look at the isotopic composition of the argon trapped in this rock, it's completely different than the Earth and identical to what we find currently on Mars. So just putting all the little bits of information together, say, yep, this is almost, we always have to say, like in everything in science, we always have to be careful, never say 100%, but almost certainly from Mars. And there's really no other candidates. An interesting question which may come up, and I'll just answer it now. How about Venus? We may have a meteorite from Venus, but the problem is we don't really know what the Venusian rocks look like. That's part of the problem. So there's only been one lander that has really photographed and sort of analyzed anything in its vicinity, and that was sent by the Russians a number of years ago, because it's such an inhospitable place. High temperatures, high pressures, high CO2. So we may have something from Venus, but we just don't know. I'm just going to put this back.
And with having samples from different bodies, Alexis brings up a good point. Have living organisms or bacteria been found on meteorites despite their ages or despite speed of travel? Have we found anything of that sort?
Okay, well, let's backtrack a little bit. I'm gonna get to that question because it's a good question, but I want to show a meteorite over here first. So there are groups of meteorites that we call carbonaceous chondrites that are water rich, that are full of organic compounds, and more importantly, if we think of the proteins in our body, they're made of amino acids. All the protein amino acids also occur in these types of meteorites, and the most famous one, which fell in 1969. I'm just going to bring this out here, and we have a whole bunch of them here. You can hear that's nitrogen. So I've just opened it, so it's pumping dry nitrogen back in there because we don't even keep this in the atmosphere for very long. These stones are black on the outside and black on the inside as well. And these are water rich, organic rich. So imagine we had an early planetesimal. So it's not even a planet, it's not big enough to be a planet. So these are 4.5 billion year old rocks. Imagine we had moisture, some warmth. We had all this organic material from our early solar system, solar nebula that sort of got incorporated into here, and things were just allowed to react. So we got hundreds of thousands of distinct organic compounds, and the very beginnings of the molecules that are necessary to form life as we know it. But we don't see anything in these, despite however hard we look, that shows anything other than simple chemical abiotics, so no life, simple chemical reactions on these bodies. So in other words, we have no evidence for anything extraterrestrial that we define as life. I also have to qualify as we define as life as we know it. We see no evidence for life as we know it in any of the meteorites that we have in our collection. So it really is, you know, and this is a question that we get asked all the time. And one of the reasons that we study these types of meteorites, these organic rich, they're very common out there as asteroids. They're very, very common. In fact, 70% of the asteroids that approximately 70% of the asteroids in the asteroid belt are probably these water organic rich asteroids that give rise to these meteorites. If you imagine the early Earth was being pummeled by these things, so the question that scientists face is, did this early delivery of this organic water-rich material, these materials to the early Earth, with all these amino acids in them, did they somehow spark life as we know it? And that's one of the perennial questions that scientists have studied. In fact, I jokingly say there's the Nobel Prize in chemistry for all of you people out there, especially for you younger school kids. You find the link, if there is a link, between what we have in here and the earliest examples of what we would consider life. There's your Nobel Prize in chemistry right there. I'm just going to put these back. In fact, it's these meteorites, it's these carbonaceous chondrite type meteorites that I feel are really going to be the stones that is going to be the bodies that propel us into our solar system. Because what's the most important thing they contain? Water. They can all you got to do is take one of those black rocks, put it in a flask, heat it to a few hundred degrees. That's not very high, and guess what? Steam comes off. So there's your main source of water out there throughout our solar system. So you could take enough. You would have to take enough. So this is actually a topic called in situ resource utilization, utilizing in situ the resources that are on the bodies that are out there. That was also one of the reasons that we have the OSIRIS-REx mission recently to Bennu, partly because it's a potentially hazardous asteroid, has the potential to impact with Earth in 100, 150 years' time, thereabouts. But also, it does represent the most basic building block materials from our early solar system that hasn't been processed, hasn't been heated to high temperatures. It hasn't been what we call differentiated into like if you think of our Earth, a metallic core and the silicate exterior. So they really are some of the most important materials to study. Any further questions? Or should I keep going? Keep going. So talking about, when we talk about the primitive materials, let's have a look. Can you see this, Alec? Can we look at this body here? So this is, if you want to come round at the sides, they don't need to see me, but I'd like them to see the rock. This is actually a slice of an ironstone. I can't lift this up because it's about 150 pounds, but you can see the outside. You can see these what are called thumbprints or regmaglyphs on the outside. This was found up by Meteor Crater, probably in the early 1900s. So this is a typical but large iron meteorite, and it's the iron meteorites represent the cores or core-like areas of these early planets. Let's call them failed planets. And this is an example of one of them. We see this beautiful metallic structure. So I don't know if you can they actually see these like linear features? Mm-hmm. If you can see these linear features, for instance, this linear feature here is a single crystal of iron. So when we see this sort of structure, which is called a Wittmann-Statten pattern, and this is one of the most common patterns that you see in the iron meteorites. This it tells you that it cooled exceedingly slowly, probably on the order of a few degrees per million years, and it tells you that it represents that core of an early extinct planetesimal. If we also look at the interior, we see other things in here as well. We see these black and golden objects. This represents, in this case, the golden object is iron sulfide. There was too much sulfur to dissolve in the metal. So as this thing was cooling, it forms little blebs in the metal. And the black here is graphite. As it was cooling, there was too much carbon. It couldn't go into the metal. sort of crystallizes out as these little graphitic things. And actually, excitingly, we actually have the Psyche mission coming up, and which is going to be launched as it next year. It's actually going to visit the largest, what's called an M-type asteroid, where we think it could represent the core of an extinct planet. You know, so far, I don't know if you've looked at it, if anyone's looked at any images. By the way, this thing's about 120 miles in diameter, so it's huge. So if you look at our best telescopic images that we have of this asteroid so far, it's nothing but a little fuzzy blob. We know virtually nothing about it. So if we think this mission is going to take off next year, it's going to take a few years to get there, and it's going to spend a considerable amount of time orbiting, getting closer and closer and closer, and really revealing what this thing looks like. We know very, very little about it. You know, we've got some estimates of the density, for instance, and density is important, by the way, because density tells us about the sort of object. So if let's move back a bit. So I'm going to struggle a little bit to lift this up. So yeah, we talk about density. So if we talk about an iron meteorite, why is this so dense? Well, it has a density of about 7 grams per centimeter cube, 8 grams per centimeter cube. Whereas if we talk about a normal stone that we lift up, it's actually quite light in comparison. So the density of an object tells us about the structure that's there. Whereas if we talk about, unfortunately, I'm gonna have to have you move back. If we move over to this, let's say Murchison again. This is really, really light in comparison, not just light in comparison to the iron meteorite, but light in comparison to the normal stony meteorites. So again, density tells us about not just the porosity of this, but about the mineralogy that was present and about the history of this material as well. Just put this back. So the Psyche mission is a really exciting mission. It's going to go to something that we know very little about, currently have very little information about, we have no good imagery of. And so one of the questions, let's say this thing is the exposed core of a large metallic object, of the center of an extinct planetesimal. What do craters even look like in an iron, in something that's largely iron? We know what they look like on the moon, which is the stony material. Well, we can replicate that in the lab. So even something as basic as what does a crater look like in an iron? Can we get craters? What sort of shape and morphology will they have? We know virtually nothing about that. So almost everything that we get from this will be exciting and new.
And on that, so I know we've been talking about the building blocks of our solar system and what we are learning from these meteorites from outside of the Earth. But David has a wonderful question in asking, are there things that we can apply on the Earth that we've learned from meteorites? So is there maybe something that you've learned from meteorites that is maybe applicable to Earth's geology or just that of the Earth?
And absolutely. So that's a great question, because look at our Earth. If our Earth likely has a metallic core, we know it has a metallic core, but guess what? We can't get down there. You know, all the knowledge that we have about our Earth comes from modeling, let's say theoretical modeling, also comes from our understanding of how something like our planet would accrete to form a metallic core, but we can't get down there. So studying the diversity of the ions that we have in our collection give us direct insights into how the cores of planetesimals and planets form. So for instance, if we look at this one here, let's look at the structure here. We get this fine Wittgenstein structure. That's telling us something about the chemistry. It's telling us something about its history and how it formed. Whereas if we look at this one here, this one I think is fascinating. This one, it doesn't have that same structure. It has a completely different structure. In fact, this whole material is a single crystal of iron. So we commonly think of single crystals of diamond or quartz or pyrite, like fool's gold, but we can get crystals of metal as well. But this thing cooled so slowly that it crystallized and then grew these meter-sized or maybe 100-meter-sized single crystals of iron. So if we look at this versus this, they have completely different structures, which means they have different chemistries. And they also probably had different histories as well. So absolutely, studying the iron meteorites gives us indications. It tells us about formation of core processes in planets. So if we have a look at one of the things I always like to point out, you know, talking about the building blocks. So this is, again, this is a carbonaceous chondrite. This one is not particularly water rich, but again, this one fell in 1969. This one has something quite amazing in it. If we always like to date things, you know, how old is something, you know, dinosaurs died out 60 million years ago, et cetera, so we put dates on things. So one of the enduring dates that we have is the first formed solids in our solar system. If we look at these little objects here, there's one here, there's one here. These are called calcium aluminum rich inclusions, but they're called CAIs. But if we radiometrically date, now what I mean by radiometrically date, I think most people are aware of carbon-14 dating. But carbon-14 dating can only be used for maybe 10,000 years or so, because carbon-14 has a relatively short half-life. Whereas in this case, we can use uranium dating. Some isotopes of uranium have half-lives of hundreds of millions or billions of years. So the little amount of uranium that's present in these things can actually be used to date these objects. And it actually turns out these objects here are the oldest objects that formed in our solar system that we can date. So everything else that we see in this room, us, the meteorites, everything else is actually younger in time. So this is the oldest material in our solar system. So we define this as time t equals 0. Everything else is then relative to that. Now, that does not mean there aren't older things, because if you think about the dust and the minerals that went into forming this, everything that was that comes here, that makes this up, actually came from other exploding stars, actually came from other star systems. So you imagine we have other star systems that you know, like a star lives its life, it has a life, it lives, it dies. When it dies, it's burnt up as hydrogen and helium. It throws those heavier elements and dust grains out into space. They then get incorporated into other molecular clouds that then condense to form solar systems. So everything in here is basically, and as you've all been, I'm sure you've all been told and heard, is stardust in one way or the other. So everything has an age that's older than the solar system, yet there's all these objects that form in our solar system and are younger in time. Okay, let's have a look over here. One of the most, I always think of one of the prettiest meteorites, and this is why we have to show this. So there's meteorite aesthetics as well. I'm going to pick this one up. I mean, if you look at this meteorite on the outside, this one's relatively heavy, okay? So it's relatively rusty looking on the outside. But when you look at the inside, let's see if we can get this. Alex, if you got, how's that? Perfect. Is that good? So this is a beautiful, one of the most beautiful meteorites, I think, in our collection. You're seeing this beautiful distribution of olivine or peridot. So it's actually the gemstone peridot distributed and within this iron matrix. So put that back down again here. So this is a group of meteorites. So we've briefly talked about stony meteorites, and we talked about the iron meteorites. But if we think about there's going to be, if we think of this large growing planetesimal, there's going to be an in-between region where we have some metal and some silicate material. And there's some theories to suggest, some people have suggested that the palisade, this is called a palisade, some people suggested that these palisades represent that core boundary between sort of the inner core of an early planetesimal and the outer silicate core. But whatever and however it forms, they are some of the most beautiful meteorites that we have in our collection. And by the way, I also like to point this out. If we look here, I have this collection. So if you think about when a typical, let's say, object comes into the atmosphere and breaks up and drops meteorites onto the ground, I think even I typically think of all the pieces that we pick up are all going to be very similar to this stone that we pick up will be very similar to this stone that we pick up. Yet this one's called Simcham, this palisade. This fell in Russia. We don't know exactly when, probably a few thousand years ago. But when they found the first masses of the material, the first big, large masses, it looks like this. It's just an iron meteorite, but an iron meteorite with an unusual composition. When they went back and started looking for more, they then started finding the palisade material. So the one with the peridot and the metal. And then as you see, each piece that they cut open has a completely different internal structure. In fact, some of them, like this one is weird. This one's metal and a mineral called chromite, so it's chromium iron oxide. And so what this really represents and tells us is that a lot of the bodies that are coming in have very different structures. So if you think of something, let's say the size of this room, which this probably was when it came in, looking from this area over here to this area over here to this area over here, would have completely different structures, though still basically made up of the same few components. So an iron, the peridot, and the chromite, and a few other minerals in there as well. So let's move back a bit. I was actually going to show, I know this is not the most interesting looking meteorite, but it's one that I just finished classifying. Now by classifying, I mean, when a meteorite comes, when we get a new meteorite, there's, what is it? You know, so what that requires us to do is to take small pieces of that meteorite, cut it, polish it, embed it in this case, it's an epoxy mount. And then we get this flat surface that I can then look at under a microscope. And in this particular case, this is one of the most recent ones we have. This fell just 3 months ago in Indonesia. So this is a small part of it that fell. So these things are falling all the time. But as you can imagine, the Earth is 70-something% water, and we've got, you know, large areas of ice and so forth. So most of the stones that fall on the Earth do not get picked up and end up either in the ocean or in places where people haven't seen. In fact, the Glendale one that fell in Glendale last year was the perfect example of how not all meteorites land with a great big fanfare. And by that, I'm thinking of the, was it 2013 Chelyabinsk, the really famous meteorite fall over southern Russia. You know, in that case, it was something about half the size of this room. So as it entered the Earth atmosphere, produced an enormous spectacle, broke into millions and millions of pieces. And also there were consequences from the sonic booms of what it did to the surrounding towns. But an awful lot of meteorites that land drop just the occasional small stone that, unless you happen to be in the right place at the right time, will never find.
Wow, thank you so much, Dr. Garvey, for your time and for taking us on this wonderful tour. As our final question to you, a couple people have asked this: how can we see more of you? How can we come tour this fall? How can we come check out this building or other buildings or other facilities that you might know of that have resources like this for others to go out and explore? Okay. Maybe you can just leave us with that.
Okay, we have a wonderful public gallery, but obviously because of the events over the last year and a half or so, it's currently not open to the public. And I encourage people to go to cc.asu.edu and have a look online. I'm expecting things will be opening up over the next few months, in which case people are welcome to come and have a look. And we also, again, will hopefully be starting up some of our public events as well. We have several events of the year where people can come and chat to us, come and see meteorites. We don't usually give tours of the vault. There are occasions where we do, but you'll just have to stay posted for that.
Well, thank you so much, Dr. Garvey, again, this wonderful experience. And thank you to Kim and Nick Estes and our wonderful cameraman, Alex, for all of your efforts. We appreciate it. And I'm going to pass things back off to Kim to finish out our webinar. Thank you.
Thanks, Alicia. I'm going to share my screen here. And we're going to start with some current events. And we're just going to touch on since it's Asteroid Day, we're going to touch on just the ASU space missions that we're on for exploring asteroids. You heard Lawrence talk about OSIRIS-REx, and Phil Christensen is the PI for the OSIRIS-REx thermal emissions spectrometer instrument. And also you heard him talk about the Psyche mission, which will be launching next summer. And Lindy Elkins-Tanton is the principal investigator, and Jim Bell is the deputy principal investigator on that. Also, we have the Lucy mission, and Phil Christensen, again, he's the PI for the Lucy thermal emission spectrometer, which is also known as LTES, and that's also going to be launching later this year. And then Hayabusa 2, our director, Minnie Wadwa, is a member of that team, and she will be part of the team that's analyzing some of the return samples from that mission. And also coming up in August, I'd like to share that Rick will be at Boyce Thompson Arboretum, and he will be doing an in-person event for navigating the night skies with them. And I'll send you guys the link tomorrow in our thank you email with how to register for that. And just a reminder that we are Still part of the Arizona Historical Society Space Exhibit, the Ready to Launch, Arizona's Place in Space. It opened back in May, it runs through November. And we encourage you to take a trip down to Tucson to see some of the things that are on display from the ASU exploration missions that we are part of. And with that, I am going to stop sharing my screen. And I will just say thank you to everyone for joining us this evening. And we invite you to come back in 2 weeks for when Rick is returning. And we're going to talk about constellations of the summer night sky and look for our survey. And please share any topics or ideas for presenters that you might like to have us have on the virtual night sky with us. And with that, I would just like to thank again Lawrence and Nick for coming along tonight and sharing all that great information. And we hope to see you guys again soon. And with that, I'm going to say thank you and good night.